Good morning, everyone. Welcome to the class of C333 Environmental Engineering 2. So today we will discuss on the waste stabilization pond. So you know that waste stabilization ponds are used to treat the sewage for the treatment of sewage, and we use what? We use microorganisms to treat the sewage here. Waste stabilization pond. So waste stabilization ponds are large, shallow basins. It's like a pond, okay, enclosed by earthen embankment in which raw sewage is treated by entirely natural process. That means using microorganisms, bacteria, algae, involving both algae and bacteria. Since this process is unaided by man, the rate of oxidation is rather slow because bacteria takes time to grow and oxidize the organic matter. That's why this process is a bit slow, and as a result, long hydraulic retention times are employed, usually 30 to 50 days, not being uncommon. That means you need a larger space for waste stabilization pond because you need to provide large retention time. Retention time means that if this is your pond, then the waste enters at time t equals to 0, like not the waste, let's say the water particle. The water particle enters here at time t equal to 0, and it travels, and the water particle exits at time t equals to t, let's say t. So the retention time here is t. This is the retention time. That means how much time the water particle remains in the pond. Since this process is slow, so you have to provide long retention time so that the waste gets in touch with the microorganisms for sufficient amount of time. That's why the size of the pond is higher. So you need large space for waste stabilization ponds. So that's a disadvantage actually. Did I make it clear?
Yes,
Yes,
sir.
The method of sewage treatment is particularly suitable for developing countries. Why? Because this is a natural process. So this is inexpensive. Inexpensive. Having tropical and hot climate. Climate is important because bacteria likes to exist in relatively warmer temperature. That's why hot or tropical climate is preferable. And where sufficient land is available, as I told you, you need large space for waste stabilization pond. Now, what are the advantages? The ponds can achieve any required degree of purification at the lowest cost. So, this is an advantage. Cost is low. Why? Because this is the natural process. You do not need to provide any um, chemicals, a large volume of chemicals. Okay, with minimum maintenance. The removal of pathogens is considerably greater than that in other methods of sewage treatment. These are able to withstand both organic and hydraulic shock load. Shock load means if there is a sudden load of waste and discharge. Then, since the pond area is or volume is large, it can absorb that shock. The ponds can effectively treat a wide variety of industrial and agricultural wastes. They can easily be designed so that the degree of treatment is altered. The method of construction is such that should at some future date the land be required for some other purpose, it is easily reclaimed. That means this land can be used for other purpose, designed can be designed accordingly for other purposes. Once the need of the waste stabilization pond are met, the algae produced in the pond are potential source of high protein food which can be conveniently exploited by fish farming. So you're using bacteria and algae. And algae is, that at micro size plant. So they actually grow in number here. So those can be used for fish culturing or fish farming. Okay. Now we used waste stabilization pond in series, like this pond, then this pond, then this pond, so this pond. These are all waste stabilization ponds. And you can see first one we call it anaerobic pond. Okay. Then the later ponds we call it maturation pond. And the in between we call it facultative pond. Okay. And characteristics of each ponds are different. I'll discuss it in later slides. So the ponds in series are more efficient in series. As you can see, they are connected in series. This is because although the hydraulic regime in the individual pond is closer to complete mixing than it is to plug flow, the overall performance of a series pond approximates that of a plug flow reactor. Now, Marai's theorem, it are you following me, guys?
Yes, sir.
Yes,
It
sir.
it tells us that the maximum efficiency in this series of ponds will be achieved if the retention time in each pond is equal. That means the size of the ponds should be equal. Only then you can achieve the maximum efficiency from the system. And this is the derivation, mathematical derivation of this theory. Let's see. This theorem states that maximum efficiency in a series pond is achieved when retention time in each pond is same. So let's say this is the load entering. Let's say this is the sewage which has 400 milligram per liter DOD, and after treatment this is the effluent concentration. What would be this concentration, guys? Larger than 400 or less than 400? Huh? Of course, you are treating the BOD, so it will be smaller, maybe 40 or 50, right? So you are reducing the BOD, right?
Yes, sir.
Yes, sir.
Okay, let's say you have two ponds only. The retention time here is T1 and the retention time here is T2. Let the retention time, okay, I already told you. And then T1 plus T2, let's say this is theta, total retention time. The efficient BOD LE from the completed mixed pond system is given below. That means the effluent BOD LE is Li divided by 1 plus K into T1 into 1 plus K into T2. Okay. Now, what is the efficiency? Efficiency means what is the percentage of removal? What is the percentage of removal? So, what is the percentage of removal? Li minus Le divided by Li into 100%. How much has been removed, guys? 400 minus 40. This is the amount Li minus Le. This is the amount which has been removed. Am I right?
Yes, sir.
Higher is the removal, higher is the efficiency. So this is the amount that is removed, and this is the division by the actual amount. So you got the fraction, and you then multiply it with 100, so you get the percentage removal. So this is basically percent removal. Hmm. So you can call it efficiency. E. E. So E is Li minus Le divided by Li into 100. Okay.
Yes, sir.
Okay. Now you might be thinking that how did I get this, right? How did I get this? We understand this, but how did we get this? I'll show you in the later slide. Let's first finish this. Le will be minimum when this will be maximum. Am I right?
Yes, sir.
This value will be minimum when this value will be maximum. Am I right?
Yes, sir.
And if this is minimum, then efficiency is what? Higher or lower? Higher
Lower.
is higher is the efficiency. Higher is the efficiency. Higher is the removal. Am I right?
Yes, sir.
And if higher is the removal, then this value will be smaller or larger. If removal is higher, then what will be this value?
Lower,
Small,
sir.
lower. So for highest efficiency, this has to be lowest or minimum. Now, if LE has to be minimum, then this has to be maximum. So let's say this is Y. Okay, this is Y. Now you know that T1 plus T2 equals to theta. So you put T2 equals to theta minus T1. This, there will be a bracket here. Now we just rearrange them. Now in your intermediate math, you know that for minimum or maximum y, the differentiation of this value should be 0. For minimum or maximum y, the differentiation should be 0, because as you can see, if this is the graph, then sorry, this is the graph, then for maximum the slope here is what, guys? 0, flat. For minimum also the slope here is what?
Zero.
0. So this is the slope. So dy by dt equals to 0 for maximum or minimum value. Can you remember that? Now, uh, you write this here. Okay. You just differentiation. You have just differentiated this and you got this value. And from here, you can write T1 equals to theta by 2 or T1 equals to T2. Now, this was for both maximum and minimum. Now, how would you know that this value was for maximum or minimum? Then you need to perform second time differentiation. And if this value, this time, if the value is negative, then that means this is for maximum. So we are differentiating this again and we found that this is negative. That means this value is for maximum efficiency. That means it tells you, it proves that in a series bond, maximum efficiency will be achieved when the detention time in each bond equals to same. Did I make it clear?
Yes, sir.
Okay. Now, I told you that this is anaerobic bond, this is maturation bond, and this is facultative bond. Now, in summary, I will discuss in detail. Just in summary, if I tell you that actually, first the load sewage enters here, and the load is here 400 milligram per liter. So, their highest load of the sewage is imposed in this pond. Now, since the strongest or highest load is imposed here, all the oxygen can be consumed by the bacteria to oxidize such a high load of DOD. That means there is no oxygen. Okay?
Yes, sir.
As it moves forward, it has already been treated. So now it has reduced the load, maybe 100, and here maybe 40. Here maybe I don't know, maybe 60, and then finally it's 40. So there are oxygen. Where?
Yes, sir.
So this is anaerobic. That means in the absence of oxygen, anaerobic. This is maturation. And what is this? This is intermediate. This has facultative. This has both anaerobic and facultative condition. Clear?
Yes, sir.
Usually at the bottom the condition is kind of anaerobic, and in the at the top the condition is aerobic. Eh, that's the overall scenario here. So anaerobic bond, first one, anaerobic one, facultative bond, and maturation bond. In the anaerobic pond, these ponds are designed to receive such a high organic loading that they are completely devoid of oxygen. They are most advantageously used to pre-treat strong wastes. So pre-treatment of strong wastes which have a high solid contents and BOD. The solids settle down to the bottom where they are digested anaerobically. The partially clarified supernatant liquor is discharged into the facultative pond for further treatment. What is supernatant? Supernatant means, if this is a glass of water and after treatment, if this is the settlement and this is the clear water at the top. So the clear water at the top is called here, this the clear water at the top is called the supernatant liquor is discharged into facultative pond for further treatment. Clear?
Yes, sir.
Anaerobic ponds are not required for the treatment of low strength sewage. So anaerobic ponds are not always required. If your sewage strength is low, then you do not need to use anaerobic pond. Okay, so suitable condition for anaerobic pond is greater than 50 degrees Celsius, temperature has to be greater than 15 degrees Celsius, pH has to be greater than 6, because these are microorganisms, the bacteria and algae, and they have a certain comfortable range of temperature and pH, like we human being have, right? Human being have a suitable temperature range. Am I right? So
Yes, sir.
similarly, they also have a suitable temperature and pH range. So it should be greater than 15 degrees Celsius and pH greater than 6 are required for delicate balance between the acid forming and methane forming bacteria. At temperature less than 15 degrees Celsius, anaerobic ponds are merely sludge storage basins. So it will not work. The microorganisms will not work at less than 15 degrees Celsius. There is no definite correlation between BOD reduction and variables that could be confidently used for design, and examination of the operational results has suggested following BOD value reduction at temperatures greater than 20 degrees Celsius. In an anaerobic condition, um, if your retention time is 1 day, this is in day, then BOD reduction is 50%. If it's 2.5 days, then BOD reduction is 60%. And these are efficiency actually. Okay, these are actually efficiency this. Okay, and if this is 5 days retention time, then variation is 70%. For the temperature in the range of 15 to 20 degrees Celsius, the BOD reduction may be estimated as 10 to 20 degrees Celsius less than these figures. Okay,
Yes, sir.
by the way, this condition is for greater than 20 degrees Celsius temperature. Okay, if the temperature is lower than 20 degrees Celsius, then this value will also be reduced. The pond become facultative for detention time more than 5 days. Okay, the rate of sludge accumulation is approximately this meter cube per hectare per year, and desludging is required when the pond is half full of sludge. The first order kinetics is applicable to bacterial reduction in anaerobic pond and can be expressed by the equation this. I'll come back here. Like, what is this NE, guys? I already told you that this is Li and this is Le. BOD, initial BOD, and this is the effluent BOD, right? Similarly, um, I talk about the microorganism. Initially, your microorganism is this, and finally, your microorganism concentration is this. Okay. So this is Li, this is NeLe. Effluent, BOD, effluent concentration of microorganism. I'm sorry, influent BOD. This is influent, which is incoming. Influent. And this is effluent. 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 And this is influent. 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 So this is influent BOD and microorganism concentration, and this is effluent BOD and effluent microorganism concentration, or fecal coliform. You can call it fecal coliform. Ni and Ne are the numbers of fecal coliform per 100 milliliter of influent and effluent respectively. This is for influent, this is for effluent. Did I make it clear?
Yes, sir.
And for Le, this is Li divided by 1 plus K into T. Hmm. And here, this is the BOD reduction rate constant. BOD reduction rate constant. And for Ne, this is Ni divided by 1 plus K into Kb into T. That means this is bacterial reduction rate constant. So this and this is different. Okay. Since this is for bacteria, so this is bacterial reduction rate constant. And since this is BOD, so this is BOD reduction rate constant. Okay. Clear?
Yes, sir.
Okay. This is simple, just that Q equals to volume by T. Q equals to volume by T. And volume equals to what? Area, cross-sectional area into depth. That's it. Clear?
Yes, sir.
Facultative bond. The facultative bond removes bulk of the BOD load. The majority of the BOD load is removed in facultative bond. The term facultative refers to a mixture of aerobic and anaerobic condition. As I told you, here both aerobic and anaerobic condition exist. Okay. So in a facultative pond, aerobic conditions are maintained in the upper layer, aerobic in the upper layer, while anaerobic condition exists towards the bottom. Although some of the oxygen required to keep the upper layers aerobic comes from reaeration through surface, most of it is supplied by photosynthetic activity of algae, which grows naturally in pond. Algae, as I told you, these are microplants. Am I right? Now, plant does what, guys? Plant does photosynthesis, right?
Yes, sir.
And through the process of photosynthesis, you produce oxygen and you consume carbon dioxide. And this oxygen that is produced by the algae are used by the bacteria to oxidize the organic matter in the pond, which grows naturally in the pond where considerable quantities of both nutrient and lights are available. Of course, photosynthesis requires light, so light has to be available here. Now, in a facultative pond, if you look at this, let waste stabilization pond. So these are like this. So this is an open area. Can you see this, guys?
Yes, sir. Yes, sir.
So this is a waste stabilization pond. This is the waste stabilization pond. And you can see these are large volume. As I told you, this needs larger space. So, okay. So as you can see, this is a waste stabilization pond. we look at Dhaka, um, sewage treatment plant, Dhaka, right? Pagla sewage treatment plant, right? In Bangladesh, we have Pagla sewage treatment plant. Let's go to the map. Pagla sewage treatment plant. Look at this. Did you see? This is a large. This is Pagla shampoo, right? Munshi Bagh. Okay. As you can see, these are large. These are the building size. Did you see? Can you see this, guys?
Yes, sir.
And look at this pond. This is huge. Okay. So Pagla waste treatment plant, and these are waste stabilization pond actually. Okay. So Dhaka was a Pagla waste treatment plant. So these are open land, so it gets sunlight. Okay. So lights are available. The pond's bacteria utilize this algal oxygen to oxidize the organic waste. One of the major end product of bacterial metabolism is carbon dioxide, which is utilized by algae. This mutual dependence of bacteria and algae is called bacteria-algae symbiosis. You know what happens, guys? Algae, right? This algae produces oxygen by the process of photosynthesis. It produces, it gives us oxygen, and it takes carbon dioxide, right? Right, guys? Am I right?
Yes, sir.
Yes, sir.
Yes, sir.
Now, bacteria takes this oxygen to oxidize the organic matter. Organic matter plus oxygen, the presence of bacteria, carbon dioxide, and water. That's how your complex organic matter are treated. It, it breaks down by the bacteria in the presence of oxygen, and it produces carbon dioxide and water and other material. And in the presence of oxygen, we have another type of bacteria, that is anaerobic bacteria. So they do not need oxygen from the outer environment. They can work in anaerobic environment. Anyway, I'm talking about the aerobic zone. Okay. And they produce what? Carbon dioxide. So they give carbon dioxide. So algae gives oxygen, take carbon dioxide. Bacteria takes oxygen, give carbon dioxide. So you can see there's a mutual relationship. This is photosynthesis and this is oxidization, or you can call it decomposition. So bacteria that does decomposition, algae does photosynthesis. So there is a symbiosis. It is mutual relationship. Both are benefited by this process. Am I right?
Yes, sir.
So this is called bacteria algae symbiosis. Algae, the presence of sunlight and oxygen. No, with the presence of sunlight, it produces new algae cell, and it produces oxygen, and that oxygen is used by the bacteria and organic matter to oxidize and form carbon dioxide and other matters and new cells of bacteria. And this carbon dioxide is used by the algae. So this is important, okay? Symbiosis of algae bacteria in stabilization pond. Wind and heat are the two factors of major importance which influence the degree of mixing that occurs within a pond. Mixing minimizes the hydraulic short circuiting and formation of stagnant regions. It ensures a reasonably uniform distribution of BOD, algae, bacteria, and oxygen. So, what they're telling here is that, uh, you know, if your load, BOD, and solid matters are here and there is nothing, that means there is a uneven distribution of load. So, in that case, load is very high here, high concentration load, very low concentration load. So that's not a good mixture actually. So you need to mix it through thoroughly if you want to have a uniformly distributed load. And if you have wind here, that wind plays a vital role to mix this load so that loads are distributed everywhere. Okay, to distribute BOD, algae, bacteria, and oxygen. The simplest approach to rational design of facultative pond is to assume that they are completely mixed reactors. If you assume that they are completely mixed reactors, but which is practically not always true, okay, just assume they are completely mixed. So, which in that case, what you can write from the first order kinetics, as I told you in the last class, that with time the BOD load, what will happen, guys? It will be reduced, am I right? Because bacteria are consuming them, right?
Yes, sir.
Okay. So, this is maybe the ultimate BOD L0. Let's say any point here. This is like Li, initial Li, okay? Li, Le, Le. And after T time, detention time. So let's see after T time, this is T by the way, time here. After T time, this has become Le. This is Li. Okay. After T time, Li has reduced to La. Now, if you take, uh, any time, let's say any point here, the slope will be what? The slope will be dl by dt. Am I right? The slope will be dl by dt. Am I right?
Yes, sir.
Yes, sir.
So this dl by dt means the rate of reduction of BOD with time. BOD reduction rate with time is proportional to the BOD remaining at this point. Let's say this is L. Let's say this is L. Clear? At any time, T, the BOD reduction rate with time is proportional to the BOD remaining at that time. Did I make it clear?
Yes, sir.
Now you can make it equals dl by dt equals by introducing a constant k. And since with time L is reducing, with time L is reducing, so you introduce a negative sign here. Okay. Now if you integrate this, if you integrate this, dl equals to minus k into L into dt. Let's write in this way. dl by L is minus k dt. Now if we integrate this from 0 to t and from Le to Li, right? Am I right? From
Yes,
Yes,
sir.
sir.
Le to Li. So you will get this, or you can write uh, this, this. Now, if the pond is properly mixed, if the pond is properly mixed, then you can write this L is equals to Le. That means if the effluent is Le, so that should be Le here also. If Le is here, then Le should also be here. So you can replace this L with Le, and then you'll get this. Le equals to Li 1 plus K T. Clear? Clear, guys?
Ji, sir.
So this was the pond, this is Li, and this is Le. Now the question is, here you have only one pond. If you had two ponds, then what would happen? That Le2 here. Then what would happen? Then it will be T1, it will be T2. Okay. So you could write Li equals to simply the same formula like this. Li divided by 1 plus k into T1 into 1 plus k into T2. Okay. K1, T1, K2, T2. If K1, K2 is equal, then you can write KT1, KT2. Clear?
Yes, sir.
And that's why I told you that I'll show you later how did I get this in Marai'S theorem. So from here, I'm sorry, this is Le. I'm sorry, this is Le. Okay, Le equals to Li 1 plus K1 T1, 1 plus K T2. If K1 equals to K2, then you can write this is K, this is K. Means K1 equals to K2 equals to K. Okay. And similarly for the this Le. Similarly for the fecal coliform, you can also write the same formula. Okay. Ne equals to Ni 1 plus K into T1, 1 plus K into, this is B, this is B, KB. This is BOD reduction rate constant, and this is bacterial reduction rate constant. Okay. Any question, guys?
No, sir.
And this is here for 20 degrees Celsius. This K, this can be changed with the temperature. So we can use this to calculate the value of K at different temperature other than 20 degrees Celsius. I showed you in the last class. So K equals to KT equals to K20 into 1.05 to the power T minus 20. Okay, so we were in the facultative pond. So in the facultative pond, in order to maintain the ponds predominantly aerobic, LE should be in the range of 50 to 70 milligram per liter. Okay, and that's why its depth should be 1.15 meter, 1 to 1.5 meter. Pond depth has to be 1 to 1.5 meter. Clear, guys?
जी सर.
Now in the maturation pond, let's talk about the maturation pond. The maturation ponds are used as a second stage to facultative pond. Their main function is the destruction of pathogens. Fecal bacteria and viruses die off reasonably quickly because they have a hospitable environment. Maturation ponds are wholly aerobic and are able to maintain aerobic if the effluent BOD from the facultative pond is low. The depth and the retention time are maintained also 1 to 1.5 meter. Similar to the facultative pond we saw, the depth is 1 to 1.5 meter. In maturation pond, we also try to maintain this depth. And we try to maintain a retention time of 7 days. Maturation ponds having retention time 5 days or less may also be chosen. The reduction of BOD and fecal bacteria in maturation ponds are obtained by appropriate version of first order kinetics applied to completely mixed reactor. I already told you that if you have multiple uh, ponds, n number of ponds, then you can write this Li equals to 1 plus KT1, 1 plus KT2, 1 plus KT3. And you know that if you maintain T1 equals to T2 equals to all value equals to T, then you can write this, right? Similarly to the bacteria, you can write this. Clear?
Yes, sir.
Okay. Now I want to show you some formula. A equals to Qt over D. This came from this. As I told you, volume equals to Q by T, and Q equals to what? Sorry, I write it wrong. Why don't you tell me? Q equals to volume by T. Volume equals to what? A into depth. Like this is the pond. This is your cross-sectional area. A. No, sorry. This is your surface area. Like this. The bottom part. This is your surface area. A. And this is your depth. So you get the volume from here. Am I right?
Yes, sir.
So you can write A equals to QT over depth. And if you rearrange this, you'll get this. And from these two equations, you'll find A equals to Q divided by D into K Li minus Le divided by Le. How? If you replace this T here, if you replace this T here, you'll get A equals to this. Okay. Another thing is to keep the facultative bond, uh, facultative characteristic, your surface loading, allowable surface loading formula is this: 20 into T minus 120 kg per hectare per day. You cannot put more load on the facultative bond. Clear? This is the lambda is allowable. Clear?
Yes, sir.
Let's say lambda is allowable. This, oh, by the way, what is T? T is actually the temperature. T is actually the temperature in degrees Celsius. Okay. Now, uh, let's say allowable load is 70 here or 60 here. Okay, kg per hectare, whatever it is. And this is your actual load. Okay, you put your Li, Q, and A, you get 80. Can you put this 80 here? Can you apply this 80 load in this pond? Your maximum allowable is 60. Can you do this? Allowable is 60.
No, sir.
It can take 60. Can you provide 80?
No, sir.
No. Then what you have to do is you have to increase your area. If you increase your area, then it might be reduced to 55. Then you can apply this. So you have to check, you have to do trial and error to see. Okay. And these are in gram per meter square per day. So we don't use we use this formula. The same formula, we are just converting the unit here. So 10 into Li into Q over A, kg per hectare per day, kg per hectare per day, same unit. Okay. So use this formula. So remember this, that lambda s equals to this. This is the your actual load that you are applying, and this is the allowable load. And this lambda s has to be less than or equal lambda allowable. Clear? This lambda s has to be less than or equal lambda s allowable. So this is the surface loading, lambda s surface loading per hectare per day, kg per hectare of what? Per hectare of area, per unit area, surface area. We can also calculate this in terms of volume, per unit volume, lambda v. Here is the formula, allowable, lambda v, and this is the area here. Anyway, so let's do some example here. The telling design a facultative and maturation pond system. So there is no anaerobic pond, only facultative and maturation pond. Are you following me, guys?
Yes, sir.
Yes, sir.
As I told you that anaerobic pond is not always required. Facultative pond, I don't know how much, how many we will need. I'm just writing randomly here. We may need more, we don't know. Okay, we may need more, we don't know. Let's see, design a facultative and maturation. So let's say this is facultative, this is maturation. Treat 10,000 meter cube per day of domestic sewage. That means Q. Whatever Q is coming, that is given. 10,000 meter cube per day of domestic sewage with a BOD5 of 630 milligram per liter. So this Li equals to 630 milligram per liter. And fecal coliform of 4 into 10 to the power 7. That means this is Ni. 4 into 10 to the power 7. The design temperature is 20 degrees Celsius. Fine. The required effluent standards are BOD5 less than 25 milligram per liter. That means you have to reduce your BOD LE here. It has to be less than or equal what, guys? 25 milligram per liter. They have told it less than, right? Let's say less than equal 25 milligram per liter. Are you following me?
Yes, sir.
And also you have a NE fecal coliform
Yes,
5000.
sir.
NE less than or equal 5000. Okay, the value of K is 0.3 and the value of KB is 2.6. So first, let's assume that we have LE 60 milligram per liter for, I mean, this facultative pond, guys. This, as I told you, that in maturation pond and in facultative pond, we try to maintain a BOD of 50 to 70. In facultative pond, we try to maintain a BOD of what, guys? 50 to 70. Clear? That means we want to maintain LE here 50 to 70. Let's say this is 60. So this will also has to be what? 60. Am I right? Right?
Yes, sir.
Yes, sir.
Remember, this effluent concentration is for this facultative pond. Whatever effluent concentration for facultative, that will be equal to Li for facultative maturation. Li for this, Le for this. Am I right? Because for this pond, this is entering. So this is Li, influent. For this pond, this is exiting. So this is effluent, right?
Yes, sir.
Okay. So we are now dealing with facultative pond. So we will call this Le as 60. Okay. So this is L equals to 60 milligram per liter. Let's say depth equals to 1.2 meter. I also told you that in facultative pond, we try to maintain a depth of 1 to 1.5 meter. Well, that's fine. Now A equals to Q over dk, Li minus Le minus 1. I already showed you that this is the formula. And I also showed you the derivation from here. Okay. So here A equals to Q by dk, Li minus Le minus 1. Now your Q is given. Your Q is, you can write this as this, no problem. So Q equals to 10,000 meter cube per day. So 10,000 Q. What is depth? I assumed it 1.2 meter. 1.2. You could have assumed 1 meter. You could have assumed 1.5 meter. No problem. Clear? Clear.
Yes, sir.
Yes, sir.
Okay. Now, guys, the values of K and KB are given and they did not say the temperature. That means these are at 20 degrees Celsius. This is also at 20 degrees Celsius. Now you have to see what is the temperature here. 20 degrees Celsius. If the temperature here was not 20 degrees Celsius, let's say 22 degrees Celsius, then what you have to do? You couldn't use this directly here. This is the value of K, 0.3, no. You have to do this. K 22 equals to K 20 into theta to the power T minus 20. Am I right?
Yes,
And this
sir.
is
Yes, sir.
zero point 0.3 at 20 degrees Celsius. This is zero point 0.3 is given. Theta, let's say this is 1.05 to the power 22, right? 22 minus 20. So this value, let's say this is a 0.35. So you have to use 0.35 here. You have to use here. But since now this is 20 degrees Celsius, we do not need to do this. Remember, temperature may not be always 20 degrees Celsius in the pond. Now this is 20 degrees Celsius in this problem. But in reality, this may not be 20 degrees Celsius. Clear? If this is not 20
Yes,
degrees
sir.
Celsius, then you have to use this and then use this converted K in this equation. For now, since the temperature is 20 degrees Celsius, zero point 0.3 is okay. So you put the value of D 1.2, you put the value of K 0.3, Li, what is Li here? 630. So you put 630 here. What is the value of Le? You have assumed 60. 60. So from here you get the surface area is this meter square. Always remember that the unit. Okay, be careful about the unit. Okay, like in this formula I showed you, in this formula Li has to be in milligram per liter. Li has to be in milligram per liter. Q has to be in meter cube per day, and area has to be in meter square. Then your lambda s will be in kg per hectare per day. Okay. So now let's see, if this is our area, then what is the surface loading? Lambda is equals to 10 into Li into Q over area. Where did I get this formula from? This 10 into Li Q over area. This lambda is. We'll calculate this and we'll ensure that this is less than the lambda is allowable. Okay. So lambda is equal to 10 into Li into Q over area. So Li, you put the value of Li. What is the value of Li, guys? 630, right? What is the value of Li? 630.
630.
What is the Q? 10,000 meter cube. What is the A? You have calculated this A here. You put this value and you'll get 240 kg per hectare per day. Remember, Q has to be in meter cube per day. You have to ensure the unit of Q is meter cube per day here, and A is in meter square and Li is in milligram per liter. Now let's calculate lambda s allowable. What is the formula of lambda s allowable? Lambda s allowable formula is this 20t minus 120. So 20t minus 120. So T is what, guys? 20 degrees Celsius in our case. So 20 degrees Celsius. 280. So lambda s is lambda s allowable. Okay? Satisfactory. Design is satisfactory. Clear?
Yes, sir.
If you
Yes, sir.
if you could find that, if you had found that this value is 200, which is less than 240, then this would be the case. Then the design will not be, is not satisfactory. Then you have to reduce this load, then less than 200, right? So what you can do, you have to reduce this load, you have to increase area. Clear?
Yes, sir.
Yes, sir.
Have to
Yes,
increase
sir.
area. If you increase the area, then you should check that what is your LE for that area from this equation. Okay. Now, all are these for what? All are these for facultative bond. We are done with facultative bond. We got the area as this meter square. We got the depth as 1.2 meter. We designed the facultative bond. Now let's come back to the maturation bond. Okay. So we don't know how much maturation bond we may need. We may need one or two maturation bonds. So let's see. Retention time in facultative bond using this formula. Okay, before I go to maturation bond, in the facultative bond we have designed area, we have designed the depth. We need to know the what is the retention time. Let's see. If you put the area here 264, and if you put the depth here 1.2 meter here, and if you put the Q here, you'll get what, guys? You'll get T. Am I right? You'll get T. Am I right?
Yes, sir.
Which is 32 days. So A, T, and D has been determined for facultative bond. Done. Now let's come back to the maturation bond. Initially, let's assume we need two maturation bonds. You could have also started with one maturation bond, no problem. Okay. So let's say assume we need two maturation bond having 7 days of retention time in each and depth equals to 1.2 meter. So you use this formula in E and LE. For LE equals to LI divided by 1 plus K T into facultative plus K into T maturation. What's happening here, guys? Here, what we are doing is we are thinking like this is a combined. How many ponds we are using, by the way? We are using two facultative ponds, right? We are using two maturation ponds. I'm sorry, we are using two maturation ponds. So there is another pond, maturation one, maturation two, and this is your effluent, Le, Ne. So if you look the whole, the all three ponds as a whole system, one single system, then what is your Le? This. What is your Li? This. What is your Li? This. What is your Le? This. Am I right? If this is a whole system, is considered one, right? Clear? Is it clear, guys?
Yes, sir.
So you can write Le, this Le equals Li divided by 1 plus K into, this is facultative, right? First it gets the facultative, so K facultative into T facultative, right? Huh?
Yes, sir.
Okay. Let's say K is same for all ponds, so we'll just write K. Then again, this is done. Now this 1 plus K into T, what is this? Maturation, right? Then the
Yes, sir.
next is what? Another maturation. 1 plus K into T maturation. Look, Li 1 plus K into T facultative, 1 plus K into T maturation square, because these two are same, right? These two are same, so you can just write square. Clear?
Yes, sir. Yes, sir. Yes, sir.
So now you write Li. What is Li, guys? Remember, you are considering the whole system as a one. So Li is this 630. 1 plus K. What is K? 0.3. Then T facultative. What is T facultative? You just calculated 32 days. This T is 32 days. And for the maturation bond, we have assumed each day needs 7. Each bond needs 7 days retention time. T equals to 7. T equals to 7. So you just put 7 here and a square. From there, you see that L equals to 6.36 milligram per liter, which is less than 25 milligram per liter. So design is satisfactory for purified. Clear? If you had found that this is 30 milligram per liter, then what you had to do is you needed to you'd increase the number of ponds, like you could use 3, or you could increase the retention time from 7 to 8 days or something like that. Okay, clear?
Yes, sir.
Going to a new pond is costly, another pond, so you could increase the 8, that the retention time to 1 days, by 1 days here. Now for the total coliform, the same formula, but instead of K you have to use KB here, and this is given 2.6 is given, 0.6, 2.6. So this is 1300, which is less than the 5000. Okay, so this is less than, so design is satisfactory. Done. Clear?
Yes, sir.
Yes, sir.
Now area of the maturation pond, you can calculate this. A equals to QT over D. What is Q? 10,000. What is T, guys? What is T here? 7 days. T is 7 days. So you put 7. And D is what? We have assumed D is 1.2 meter. So you put 1.2 meter. So area equals to 58,000 meters square. So this area is this area and this area is same, which is 58,000 meter square. Depth equals to 1.2 meter and T equals to 7 days. And for this pond, area equals to what, guys? 264,000 meters square. Depth is again 1.2 meter and T equals to 32 days. So this is for this pond and this is for in each of this pond. In each of this pond. Clear?
Yes, sir.
This and this corresponds to this. This and this corresponds to this.
And facultative. Facultative pond corresponds to this. Okay. Any question? Any question?
No, sir.
Okay then. Thank you very much. Have a good one and stay safe.